In this lecture, we will define sampling distribution and sampling distribution of the mean, discuss the central limit theorem, calculate a standard error of the mean either from a sigma and n or from sample data, and describe the effect of n on the standard error of the mean. In all of our previous scenarios, we were interested in comparing one observation to a group of other observations. For example, when you plot the SAT math scores for all the students who took the exam in one year, you can make statements about how well one student performed in comparison to the rest of the students. Let's draw a normal curve with a mean of 500 and a standard deviation of 100. If a student scores a 600 on the exam, his score is one standard deviation above the mean, placing that student in the 84th percentile. In other words, with a score of 600, he performed better than 84% of the rest of the students taking the exam that year. Now, instead of comparing one score to others, we are going to take a sample of scores, calculate its mean, and, eventually, make predictions about the larger population based on the value of the sample mean and the standard deviation of sample means. If you calculate the values for the mean of many samples and plot those values, you will make a new distribution with a mean and standard deviation of its own. However, because you are plotting the means of numerous samples, the standard deviation of this new distribution will not be the same as the standard deviation of the individual observations. Instead, the standard deviation is calculated by dividing the population standard deviation by the square root of the number of observations in each sample. To help us understand this concept, let us imagine that instead of just taking one sample, we repeat the sampling process infinite times. From each repetition, we calculate and record the value of the sample mean so that we now have many observations of x bar. We can then calculate the mean and the standard deviations of all these means. We can also draw a histogram to see their shape. In other words, we can describe the sampling distributions of the means using three of its most important characteristics: its mean, its standard deviation, and its shape. Let's look at a nifty applet I found online. The simulation is set initially to sample 5 numbers from the population, compute the mean of those 5 numbers, and then plot that mean. I'm going to click the animated sample button, and you will see 5 numbers appear in the histogram. The mean of the 5 numbers is computed, and then that mean is plotted in a third histogram. If I do this several times, you can see the distribution of means beginning to form. Now that we've seen how this works, I'm going to speed things up a little bit by taking many samples at a time. Notice that as I increase the sample size, regardless of the histogram of the sample selected that's created, the distribution of the sample means becomes more bell-shaped. This is the theoretical meaning behind something called the central limit theorem. As sample size increases, the distribution of sample means will more closely approximate a normal distribution. Another assumption that this theory allows for is that the value for the population mean, mu, can be approximated by the mean of the sample means. This is really a significant point because we're often trying to determine the value of the population mean, and except in very rare cases, you cannot ever determine the true value of mu because you simply don't have access to the entire population's scores. We'll continue to explore this concept of inferring the population mean from a sample mean when we studied statistical tests of inference coming up in this course. This diagram shows how the standard deviation of the two curves differ. The shorter curve, colored in dark orange, represents the distribution of individual scores, like we've been working with up until this point in the course. The mean and the standard deviation of this distribution appear to be 25 and 7 respectively. However, if you take many samples of n equals 10 and plot those sample means in a separate histogram, the mean will theoretically remain the same, but the standard deviation will always decrease. Remember, the standard deviation describes the spread of the values around the mean. If you plot the distribution of sample means, you've already reduced the variability of the scores because, in this example, each score represents an average of 10 scores. For example, using the scale for the dark orange distribution, where the values seem to range from around 5 to 45, if a random sample of n equals 10 scores were selected, the sample might look something like this: 10, 44, 34, 22, 20, 30, 18, 6, 23, and 38. The sum of these 10 scores is 245. Dividing the total by 10, because there were, 10 observations, results in a sample mean of 24.5. If this process were repeated over and over with new samples of n equals 10, you might get such values for the means as 26.2, 27.0, 21.8, 33.6, 31.1, etc. The important thing to note is that each of these sample means has kind of averaged out the really low or really high values in the sample. Thus, the distribution of sample means will have less variance, and consequently, a smaller value for the standard deviation, which we now call the standard deviations of sample means, or the standard error of the mean. And it is represented by the symbol sigma sub x bar. You're going to need to be able to calculate the standard error of sample means. If you happen to know the population standard deviation and the sample size, the math is actually really straightforward. It's just a division by the square root of n of the standard deviation. But remember, this whole thing is based on the premise that we're going to be making some predictions about a population, which means that we probably won't have the population standard deviation. Instead, we'll have our sample. And our sample, those data, if we want to use them to predict the population standard deviation, that's when we have to calculate S hat, if you'll recall from a couple chapters ago. S hat can be calculated from raw scores using the formula on the left, or from the data that's been summed up and squared and summed up using the equation on the right-hand side. So let's practice calculating the standard error when we do actually know the population standard deviation. Population parameters for scores on the Stanford-Binet IQ test have a mean of 100 and a standard deviation of 15. If you were to take a random sample from the population of a size of 20, what's the standard error? And then I want to follow that up by calculating what if n were 40, because something really interesting happens as n increases. And we talked about it a little bit a couple slides ago, but now I'm going to show it to you in more detail. Let's begin with the first one where I have an n of 20. If n equals 20, and I know the population standard deviation is 15, then to solve for the standard error of sample means, I just need to take 15 and divide it by the square root of 20. Now when I type this in my calculator, I want to be careful that the square root of 20, when I do the division, that it's not like doing some weird order of operations something. So I want to kind of make an estimate in my head first. I know that 3 squared is 9, and 4 squared is 16, and 5 squared is 25. So that means the square root of 20 needs to be a number somewhere between 4 and 5, because 16 is less than 20 and 25 is greater than 20, so the square root must be somewhere in between. So if I had 15 divided by 5, the answer would be 3. If I had it divided by 4 on the bottom, the answer would be like 3 point something. So I'm really making sure that I have an answer for sigma sub x bar somewhere between 3 and 4, and sure enough, I've got 3.3541 as my answer. And I'm going to go ahead and keep 2 decimal places. So I underline what I keep. Look next door. I do not round. So that means that my answer for sigma sub x bar, if n equals 20, is 3.35. Okay. Now let's do the same game, except for this time for a larger n. Okay. So with my larger n, my sigma is still the same because that was the population standard deviation of 15. Now I'm going to divide by the square root of 40. Playing that same game, 6 squared was 36 and 7 squared is 49. So I'm expecting the denominator now to be something between 6 and 7. So I better get somewhere around 2 point something as my answer when I take 15 divided by the square root of 40 in my calculator. And sure enough, I get 2.3717. Again, check for rounding. We do not round. Remember, you just look one number next door. Don't look 2 numbers and start doing double bumps. All right, one number next door to that second digit. So my answer when n equals 40 is 2.37. So if for the blue sample, this was for n equals 20 and purple was n equals 40, I can now make a general statement as n increases, sigma sub x bar decreases. Let's do one more example, and this time let's work with data that are derived from raw data rather than population data. In this example, I've been given the same kind of prompt. We're working with Stanford-Binet IQ scores. However, we're working with a very specific sample, and in this sample, n equals 10. And I'm expecting that because these kiddos are at a fancy schmancy, gifted, and talented private school, that they're actually going to end up with a mean that's higher than the population mean of 200 or 100 rather. So the sum of squares and the sum of the actual values, the scores, is given to me. And I want to calculate the standard error. Now the standard error is sigma sub x bar. But because this time I don't have population data, I have sample data, I'm actually going to use those sample data pieces to calculate S hat. And then I'm going to use S hat in place of sigma in sigma sub x bar. So let's just do this. I've chosen this formula because it matches the data that we're given. And this looks a lot like the ones that are on your concept check this week, 8B. So I'm going to start off by just doing some substitution. Under my square root in the numerator, the first thing I have is the sum of the squared values of x. So I'm going to put that in 2, 4, 4, 4, 6, 1. And now I'm subtracting on top. It's the sum of x quantities squared. So it's going to be 1543 squared all over n, which is 10. And then the whole numerator is over 10 minus 1, because remember, we're calculating S hat. So I'm going to do the term on the numerator first, that has the square in it. So I'm going to take 1543 and square it. And then dividing by 10, I just need to move that decimal place a little bit. So here's what it's going to look like. I'm going to have 24,4461 minus 238,084.9, because that dividing by 10 moved my decimal place. And then, of course, n minus 1, whoops, I don't know why I wrote 9 there. Oh, I know why. My brain got ahead of my pen. 10 minus 1, of course, equals 9. So I'm going to type 244461 minus 238,084.9. Divide that by 9. And I'm going to keep working here up top. That gives me the square root of 708 and change. A lot of 5s there repeating. So I'm going to do the square root of that. And it gives me 26.6168. Now you want to, on all of these problems where you have these funky old decimals, you really want to be careful and keep the decimals for 4 or 5 places out, so that when you actually then now put this S hat into the standard error calculation, you don't have rounding that affects your answer. Okay, so just make a habit out of keeping 4 or 5 decimals. I might even keep just one more just for kicks and giggles, and it would be a 2. So now I'm going to be ready to use the second equation to find my actual sigma sub x bar, remembering that I'm replacing the population standard deviation on top with my estimate, which is 26.61682, and I divide this just by the root of n being 10. So I'm going to divide by the square root of 10, and I get a sigma sub x bar of 8.4169. And then if I do my rounding, keep 2 decimals, just kind of as a general rule, it works out. I see that the number next door to my 1 is a 6. Remember, don't look beyond that, just look one number to the right. And I see that, yes, I do need to round, and so my sigma sub x bar value, the answer to this question, is 8.42. And that agrees with the idea that the standard deviation of just the population was 15. Because we're dealing with a sample and sample means, it should go down, and it did go down all the way to 8.42. Regardless of the scores that they had, it was going to go down.
The sampling distribution of x bar is normal if the underlying population itself has a normal distribution. And let's take this a little bit further. What happens when the population distribution is not normal? Because even though many things in nature fit a normal distribution, there are an awful lot of cases where we're working with populations that are simply not normally distributed. They're skewed, they're bimodal, they're rectangular, something along those lines, but regardless, they're certainly not normal. So to take a look at this, let's go back to that applet that we used earlier today. Okay, so back in the applet, this time I'm going to change the first distribution setting so that I can look at, let's start with just a skewed distribution. So it happened to give me a positively skewed distribution, meaning most of the scores are at the low end of the spectrum. So let's just do an animated sample like before, and you can see that 2 of the scores came out from the low end, 2 came towards the right-ish, and then 1 came out from the extreme, and it plotted me a mean. Okay, that's fine. Let's do another one. This time, all 5 of the scores came from the hump region of the original distribution. That seems a little bit more likely, but obviously we're working with a random sample here, so of course it's going to be where it's going to be. But because there are simply more scores at the high end of the hump, so the low end of the actual distribution, I would expect more scores on average to come out on the low end. So let's do that again. You can see how different that mean is. And again, this time, 4 out of the 5 scores came from the region where the most scores were. And it plotted my mean. And I'm going to do several of these just kind of quickly. And you can kind of see that originally they're falling typically towards the left-hand side, which makes sense. You can also see in the distribution of means how it's starting to form, well, it certainly isn't normal yet, but it's starting to look like there's going to be some sort of a center and some sort of tails. All right, Now that I've done that slowly, I'm going to switch to 1,000. And gosh, now it's much more obvious. I still have the majority of my scores coming from the low end of the original parent population, which is obvious because the mean itself is towards the low end, just like that parent population. Let's do another 1,000. And it's becoming more and more normal looking. Let's go by 10,000s. I'm up to 15,000 reps is what they're calling it now, or samples. Here's another 10,000 up to 25,000. And as my n gets higher and higher, just as promised, the distribution becomes more and more normal. So shockingly, this shows us that a non-normal parent population can actually produce a normal distribution of means. Let's do another one. Let's do another weird one. How about uniform? In a uniform distribution, I would expect all my samples to kind of look random. That first one looked weird, but you know, hey, if you've ever watched a roulette board, you know that random doesn't mean it always looks like they're different. Random simply means everything had an equal chance of being chosen. Yep, that one looked really random. There we go. And I can see now I'm starting to get another sort of distribution forming. Let's go faster. Ah, interesting, isn't it? Because now what it's doing is it's becoming more and more like the middle, because even if you take from the left and take from the far right, they average out to give you something middle-ish. So all of the samples, even if they give you, like this one, some low scores and some very high scores, their average still puts you somewhere in the middle of the middle. So for a uniform distribution, or what we've been calling a rectangular distribution, we get, again, a normal distribution of sample means. Let's do a weird one. Let's go big, nice bimodal, okay, with some gaps. Poor thing's lost a few teeth. So I would expect the majority of my random samples to come from the hump regions. And true to form, this seems to be happening. And I get myself some means that are falling in the middle, and we go again to a fast. And 10,000 samples shows me already very easily fitting a normal distribution. So this is the central limit theorem in action. Not only will a distribution of sample means become normal from a normal population, but a non-normal parent population will also produce a normal mean distribution of sample means. Very cool. In summary, the sample mean x bar of a simple random sample, SRS, of size n drawn from a large population with a mean of mu and a standard deviation sigma has its own sampling distribution with the same mean mu and a narrower standard deviation now represented by sigma sub x bar called the standard error. The sample mean x bar actually gets used as an unbiased estimator of the population mean mu. Remember, the population mean is the thing that we almost always don't know. So using x bar as the estimator makes sense according to the central limit theorem. And this population mean mu, that distribution has less variability than a single observation would. And finally, as the sample size increases, the sigma sub x bar decreases because you're dividing by a larger number, which makes the quotient, the thing that you get after you hit divide enter, that makes that get smaller. On the flip side, if n were to get smaller, then you're dividing by a smaller number and the overall quotient would get larger. So sigma sub x bar, or the standard error, would actually increase.